Well, hello everybody, and welcome back to, now we're on Chapter 6, the normal curve, standardization, and z-scores. This is our last chapter before our first exam, so this will be the last material that you'll need to cover before studying for the test. So, we're going to start talking about the normal curve, standardization, z-scores, and the normal curve, and then in a separate lecture we'll talk about the central limit theorem. So we're going to start reviewing shapes of distributions. We already talked about this, but frequency distributions, just to recap, are a way to show all the scores in either a sample or population and how many people received each score. So sorry, in this case, this is a frequency distribution. We've got test scores here. The lowest score someone received was a 6. The highest score is a 10. And frequency on the y-axis, so we have 6 people receiving a score of 6, 7 people obtaining a score of 7, 9 people obtaining a score of 8, and so on. This would actually, or should be, a histogram. I don't know if you noticed that there's a problem with my graph here, and that is that in a histogram, the bars should be touching each other, and that is true. In this case, the bars should be touching each other. I made a little mistake on this graph. And a histogram is created when your values are numeric values, numbers. And bar graphs, which is what this actually is with the bars not touching each other, are used when your data down here are nominal or categorical, when people fall into different categories like eye color or hair color or something like that. So anyhow, this is a should be a histogram, even though the bars are not touching each other, pretend they are. Now, you can smooth out the histogram to make a curve, and from now on in this class, we're going to be looking at curves that look a lot like this. These are histograms. So again, down here is, in this case, test scores. We had quiz scores on the last slide. On the y-axis is frequency, or number of cases. And then what we've done is just smoothed out the bars from a histogram to make a curve. So instead of being actual bars, this kind of like jagged pattern, we've smoothed them out to make a curve, but it's the same information that you can see. Most people got scores around 75. Much fewer people got scores around 50 on this test, and many, many fewer got scores in the 90s. So this is just a histogram represented as a smoothed out curve. And if I were to ask you, what is represented by this part here, the part of the graph that's under the curve? Well, the part of the graph that's under the curve is really representing all of your data. All of your cases fall under the curve. We don't typically draw the curves with all these little dots under here representing all your data, but that's really what's under there, is all your data points. And as you can see, there's many, many data points here at the highest peak, the mode of the curve, and much fewer data points, many fewer data points down here at the tails. Okay? Also, to recap again, we talked about shapes of distributions, and the distribution shape depends a lot on the standard deviation. So in this first graph here, we have a large standard deviation. The mean is right here in the middle. A large standard deviation, which means lots of variability, that the data is very spread out. And when you have a large standard deviation, you have this very kind of short and wide curve. That's showing us that we've got a lot of data points, but they're all spread out. They're all over the place. We don't have them clustered in one main area. The large standard deviation is showing that this curve is representing very spread out data, and you get the short, wide curve. If you have a very small standard deviation in your data set, that's showing us that there's very little variability, that the scores are all clustered together. And when you have a case like that, your curve looks like this. It's very tall and kind of thin. And that's showing that most of your data fall here right near the mean, and there's very little data that falls outside of that. And here we've got what looks like a normal curve somewhere in the middle. and we're going to talk about that in a second. This is sort of a bad slide, but this is just the examples of some different curves and different distributions and how they affect the shape of the distribution. Very often we're going to be comparing two distributions of scores. So maybe we want to compare males and females and their scores on a statistics test, or freshmen versus seniors and compare their GPAs or something like that. We're often looking at two different distributions. And so you can see in this case up here at the top, we have two distributions. The means are different. This curve has a lower mean than this curve here on the right, has a higher mean. But the standard deviation is the same, and you can tell that because the shape of the distributions are the same. So the variability between the two distributions are the same, but we've got two different means. One distribution has a higher mean than the other. In this middle case, we have two distributions. In this case, they both have the same mean. So both groups are performing the same average score. But you can see we've got one distribution with a lot more variability. This is that wide, short, and kind of wide curve. And we have one distribution with very little variability, a small standard deviation, and this is this tall, thin curve. And lastly, down here we have an example, and in this case we've got two curves, two distributions. They have different means. This mean on the curve on the right is higher than this mean for the one on the left. And the curve on the right has a larger standard deviation. There's more variability compared to this one on the left. So this is how variability impacts the shape of curves. And lastly, as a review, we also talked about skewed distributions. And so we talked about negatively skewed and positively skewed distributions. A negatively skewed distribution looks like this one here on the left, where you have most of your scores high up here in the, many people scored in the high range, but you have a few very low scores, a few outliers, and that is pulling this curve in the negative direction, and we call that a negatively skewed distribution. And we talked about a positively skewed distribution where you have most of your data points kind of falling low here on the scale, but we have a few very high outliers, and this is pulling this distribution in the positive direction, and we call this a positively skewed distribution. And the one in the middle here is normal. We call this not skewed. This is a symmetrical distribution, and this is the one we're going to be talking about for pretty much the rest of the class. Aside from on this exam, this upcoming exam where I'm going to ask you, I can pretty much guarantee, something about a negatively skewed or a positively skewed distribution. From now on, every curve we're going to be talking about will be normally distributed. So what is a normal curve? Well, it's a very special curve. It is specific in that it is bell-shaped. It's the shape of a bell. It is unimodal, meaning it has one mode. And it is symmetric, meaning that if you folded the curve, and I'll do that right here, right down the middle, the two halves would lie right on top of each other. So we call that symmetric. And it's defined with very specific mathematical properties that we will use as we move on into our inferential statistics. The distributions of many variables approximate a normal curve, and this is correct. The more data that we collect, what we find is that many variables fall into a normal distribution. So if we collected heights of people or weights of people or IQ, all of these things, if you collect enough data, tend to fall into a normal curve. And so even though we may not collect enough data to actually see the normal curve ourselves, we assume that the data underlying, or the population of data underlying the sample of data we take is in a normally distributed shape. And you can see here, this is from your book, when you have a small sample, in this case we have 5 students, and we're looking at height. So height is down here. On the x-axis, frequency again on the y-axis. And when you only have 5 students, it doesn't look very normal at all. As you now get more data, now we have 30 students, the distribution starts to look a little more normal. And then if you get all of this data, that's 140 students, it becomes even more normal. And as you collect more and more data points, we would see that we would get this normal curve starting to form. Okay, so some special properties about the normal curve. Like I said, it's symmetrical, which means 50% of the cases are above the mean and 50% of the cases are below the mean. That's important. The mean, median, and mode are all the same, and they're all at the very height of the normal distribution, which is right in the center. And as I said, the normal curve has a precise mathematical function that's defined by the mean and standard deviation of the distribution. So here we have a normal curve, and as I jokingly wrote, a statistics student's best friend. I'm not sure if this will turn out to be your best friend, but it will certainly be important for you as we go through this class. Here's our normal curve. It is bell-shaped. It is unimodal. Here's the mode right in the middle. It is symmetrical, meaning 50% of the cases are below the mean and 50% of the cases are above the mean. And then there is a specific property that we know about normal curves. We call it the 1, 2, 3 rule. And what you can see here, this is 1, this plus 1 here. This means 1 standard deviation above the mean. And this minus 1 is 1 standard deviation below the mean. And we know, based on the mathematical properties of a normal curve, that between 1 standard deviation above and 1 standard deviation below lie 68% of the cases. We also know that, here's the 2 part of the 1, 2, 3 rule, that within 2 standard deviations above and 2 standard deviations below, that comprises 95% of your cases. Almost all of the cases fall between plus and minus 2 standard deviations. And if you go out to 3 standard deviations above and 3 standard deviations below, you can see virtually all of your data here is here. 99% of your cases will fall within plus or minus 3 standard deviations, with only 0.5% being greater than 3 standard deviations and 0.5% falling out here at less than 3 standard deviations. So the 1, 2, 3 rule, I have it right here. This is for a normal curve, so if you're talking about a skewed distribution, this does not hold up. But for a normal curve, 1 standard deviation on either side of the mean will encompass 68% of the cases. 2 standard deviations on either side of the mean on a normal curve will encompass 95% of your cases. And 3 standard deviations on either side of the mean of a normal curve will encompass 99% of the cases. And as I said, you have to remember there are 50% of the cases on either side of the mean. So if you can remember that information, let's say we know that test results for a specific test are normally distributed, meaning they fall in a normal curve. And let's say you scored 1 standard deviation above the mean. What percentage of scores are below your score? And what percentage of scores are above your score? So if you scored at 1 standard deviation above the mean, what percentage of scores are below your score? What percentage of scores are above your score? You might want to take a look at this. Maybe pause for a minute and try to figure it out. If you scored right here at 1 standard deviation above the mean, what percent of cases are below yours and what percent of cases are above yours? So pause to figure it out. And now I will tell you, you're back. The answer is 84% of the cases are below you. So remember, you scored here at 1 standard deviation. We know 50% of the cases fall below the mean, so this whole part here is 50%, plus 34% right here to get to your 1 standard deviation. So 50 plus 34 gives you 84%. So you scored above 85% of the, or excuse me, 84% of the individuals on this test. And how many are above your score? Well, the total amount in a distribution is 100%, minus the 84 that are below you, so 16% are above you. Or, of course, you could add these up and get 16%. So I have this for you here. 50% is the lower half of the curve. 34% is the percent between the mean and one standard deviation above the mean. So 84 of the cases would be below one standard deviation above the mean, so below your score, and 16% would be above your score. If you figured that out, good for you, and it means you already know quite a bit about the normal curve, so good job. Now we're going to take this a step further into a theoretical area. So bear with me as we start talking about the standardized normal curve. The standardized normal curve is theoretical, which means we don't actually gather data to compute this standardized normal curve. It's theoretical. Statisticians and mathematicians have modeled this, and they are sure of its properties. This is our standardized normal curve here. It's based on an infinite number of cases. So remember, down here, this is basically a histogram, and you have anything that you're interested in studying. If you're studying heights of people or weights of people, like I said, or IQ, or income, or whatever it might be, doesn't matter. And it's based on an infinite number of cases. If we collected cases to infinity, which of course we never do because quite literally it would take forever, but if we kept on collecting data, what we would get would be this normally shaped distribution. And it's represented by a distribution by a curve that doesn't touch the x-axis. You can see how it's floating a little bit above the x-axis, which is showing us that this is theoretical, that is infinite, and we could always collect more cases. There could always be another case over here on the left and always be another case on the right, theoretically. So this is sort of how we represent it. In a standardized normal curve, the mean of a standardized normal curve is always 0. Okay, and I'm going to show you how we transform the scores to make it that way. But just know, no matter what we're looking at here, the mean of a standardized normal curve is always 0. Therefore, it makes sense that any point above the mean is going to be a positive number, positive 1, positive 2, or any type of fraction or decimal place in here. And any point below the mean, again, because the mean is 0, will be negative. And we are, with a standardized normal curve, as I said, the mean is 0, and the standard deviation is equal to 1. So this plus 1 here, that represents 1 standard deviation above the mean. This plus 2 were 2 standard deviations above the mean. Plus 3 were 3 standard deviations above the mean, and same in the negative direction. Negative 1 standard deviation below the mean, 2 standard deviations below the mean, etc. Which brings us to the idea of z-scores. Z-scores are incredibly important. As we start talking about them, you may think to yourself, why, oh why is she making me learn this? They will be incredibly important for us, and you'll see their value probably by the end of this lecture, so stick with me on this. So imagine that you're looking at our standardized normal curve. You see a 0 in the middle at the baseline, and then there are an infinite number of little marks going off to the right or left. We call these little marks z-scores. So what I'm describing here is, again, you're looking at this. Here's the 0 in the middle, and while I've only marked here on this graph positive 1, positive 2, positive 3, you could imagine any number of little tiny marks here, right? Someone could get a score of 0.5, 0.83, 1.23, 2.83, forever. All these little teeny tiny places, people can score anywhere between 0 and as far as this will go, and same in the negative direction. And basically, these little marks that we have at the bottom here we call them z-scores. Z-scores to the right of the mean are all positive, and we've said that. I went backwards and I guess I went forward, sorry. Z-scores to the right of the mean are all positive, and that is true. So again, the mean is 0, and any score over here to the right of the mean will be a positive z-score. Any score to the left of the mean will always be a negative z-score. And so if you got a z-score of +1, so these numbers here, +1, +2, +3, these are actually z-scores. -1, -2, -3, these are z-scores. So if you got a z-score of +1, it would tell us that you scored 1 standard deviation above the mean. If you got a z-score of -2, it would mean that you scored 2 standard deviations below the mean. Z-scores are on what we call standard deviation units. So if you have a z-score of 2, you are 2 standard deviations above the mean. This is what we just said. Z-score of -1 means you're 1 standard deviation below the mean. What would a z-score of 0 mean? Well, hopefully you guessed. A z-score of 0 means that you scored right at the mean. You're right average. And in fact, as I'm a neuropsychologist, we do a lot of testing with individuals, kids, and adults, and sometimes the tests are scored on a z-score scale. And so if you tell a parent, let's say, that their child got a z-score of 0 on a test, very often parents will say, "What? My child got a 0? That can't be good." But it's a z-score of 0, which actually means they're doing great. They're right average, they're right on track, everything's fine. So knowing about z-scores can be very helpful. So z-scores, when a set of data are normally distributed, we can standardize each score by converting it into a z-score, and I'll show you how to do that. Why would we want to transform scores into z-scores? Because we can measure data or compare data that are measured on different scales, and I will show you how we do that very soon. But think about this for a second. By itself, a raw score, an x value, we call our raw scores x's in statistics, provide very little information about that score. So if I told you I got a score on my Spanish test and I got a 53, I'm not saying 53%, I'm just saying I got a 53. We don't know what that means. It could be I got a 53 and maybe it was out of 55 points and I did amazing. Or it could be that the test was out of 150 points and I got a 53, and that's not so good. So raw scores by themselves tell us very little. But if we transform the raw score into a z-score, which is a standardized score, and it's standardized on standard deviation units, all of a sudden it tells us a lot more. And as we've said here, a z-score reflects how many standard deviations above or below the mean a raw score is. A z-score is positive if the score lies above the mean, and a z-score is negative if the data value lies below the mean. So the process of changing x into a z-score, again, depending on if it's positive or negative, it's going to tell you whether or not that value is above or below the mean. And the numerical value of your z-score tells you how many standard deviations between that score and the mean. So I've said that quite a bit. And again, here it is again. A z-score that's located 2 standard deviations above the mean will have a z-score +2. And that always means 2 standard deviations above the mean. So let's see how we calculate it after I've said what it means. Here's the formula. Z-score equals the score minus this is mu, mean of the population, divided by sigma, which is standard deviation of the population. Remember, if we're using mu and sigma, it means these are population symbols, and it means we're talking about a population. So the score minus the population mean over the standard deviation of the population. So let's try this. Get out your calculator if you don't have it already. Suppose you know that SAT scores among college students are normally distributed with a mean of 500 and a standard deviation of 100. If the student scores a 700, what would be her z-score? So pause me here for a second and try to figure out the z-score here. All right, and if you've done this, how would we do it? Z-score is the x-score of 700 minus the mean of the population mu, which is 500. We said the mean of 500, and divided that by the standard deviation of the population, or sigma. Standard deviation is 100, so we divide by that. So 700 minus 500 is 200, divided by 100 is 2. So what does that tell us? It tells us her z-score would be 2, which means that that individual's score is 2 standard deviations above the mean, and she should be very happy with herself. Here's where z-scores can get a little interesting and can help us quite a bit. We said that they're very useful for comparing two sets of data with different properties. So let's say you have a set of math test scores that has a mean of 70 and a standard deviation of 8. There's a set of English test scores that has a mean of 74 and a standard deviation of 16. Let's say you took both of these tests and you got a 78 on both. You got a 78 on your math test and a 78 on your English test. The question is, for which test would a score of 78 have a higher standing? Meaning, which one should you be happier with? Your score of 78 on the math test or a score of 78 on the English test? Again, pause this here. Try to work this out. How would you do this? You would be finding a z-score for the math test. Score of 78, and you're also going to find a z-score for your English test, where you got a 78. So go ahead and compute those two z-scores, and pause that until you've done it. So you would need to find the z-score for each test. For the math z-score, you got a 78. The mean was 70. So 78 minus 70 divided by sigma, or the standard deviation, which is 8. That gives you a z-score of 1. For the English z-score, that's a 78, same score, minus the mean on the English test of 74, divided by the standard deviation for the English test, which is 16, which gives you a z-score of 0.25. So the question is, which test result would you be happier with, your math or your English? Well, the math score would have the highest standing since it is 1 standard deviation above the mean. The English test score is only 0.25 standard deviations above the mean. So in each case you scored above the mean, but in your math, that was 1 standard deviation above the mean, with English only 0.25 standard deviations above the mean. So you should be happier with your math test. All right, what about this? What if we tried to solve for something else in that equation? This is going to bring you back to maybe some high school math that we hopefully can remember. And don't worry, I'll help you through it. What will be the miles per gallon for a Toyota Camry when the average miles per gallon is 23? It has a z-value of 1.5 and a standard deviation of 2. So now we know the z-value. We know the standard deviation, we know sigma, we know mu, and we're looking for x. We're trying to solve for x. So if you can plug those values into the equation and cross-multiply, you might remember that term, try to solve for x in that equation. Again, pause here. And then if you've solved, we have this formula. We plug in what we know. We know the z is 1.5, z-value of 1.5. We're solving for x minus mu. Mu is the average, the population mean, which we're saying is 23, divided by the population standard deviation, which is 2. When you cross multiply, remember you would take 1.5 and multiply by 2. which gives you 3 equal to x minus 23. And to get x by itself, we've got to add 23 to this side, add 23 to this side, and x equals 26. Now, some of you are saying, oh my goodness, cross multiplying. You can't make me do that. Oh, there you go. Camry would be expected to use 26 miles per gallon of gasoline. And anyhow, if you are upset about the cross multiplying, don't worry, I won't make you do it. There's actually a formula. This is the formula if you want to solve for x and you happen to know z and sigma, the standard deviation, and mu. This is what we just did. But I wanted to show you that this is not some kind of special magical formula. It's actually just a transformation of the original z formula that we had. Just to get this, they cross multiplied. You can use this and not have to worry about it. Okay. A group of data with a normal distribution has a mean of 45. If one element of the data is 60, will the z-score be positive or negative? Well, you should be able to look at this and figure it out. If the mean is 45 and somebody scored a 60, which is above the mean, you know the z-score will be positive. All right, the z-score must be positive because the element of the data set is above the mean. Z-scores and locations. In addition to knowing the basic definition for z-score, it's helpful to be able to visualize z-scores as locations in a distribution. Remember, z equals 0, that's the center, that's the mean, and the tails correspond to plus or minus 2 standard deviations. And if you remember, what percent of cases fall between plus or minus 2 standard deviations? Hopefully you remembered, and the answer is 95% of cases. And then more extreme z-score values are possible. Even though more extreme values are possible, most of the distribution is contained between plus and minus 2 for the z-score. And really almost all scores are between 3 and negative 3 z's, a z-score of 3 and negative 3. If you remember, 99% of the cases fall there. We're rounding, we're going to just not use the decimals, but really the vast majority of the cases with only a few, 0.5% falling above a z-score of positive 3 or below a z-score of negative 3. So transforming z-scores into percentiles, you've probably heard the term percentile before. What's a percentile? A percentile tells you what percent of the distribution you have scored above. So if you took a test and you scored in the 80th percentile, it means that you scored above 80% of the people who took the test, and 20% scored above you. If you're in the 40th percentile, it means you've scored above 40% of the people who took the test, and 60% scored above you. And of course, if you scored at the 50th percentile, you're right in the middle. You've scored above 50% of the people who took the test, and 50% scored above you. And you can use the area under the curve in the 1, 2, 3 rule that we've talked about to calculate percentiles. So here we are again. Here's now our z-scores. We can call these z-scores. Z-score of 0, meaning you're right at the mean. A z-score of 1, 1 standard deviation above the mean. A z-score of negative 1, 1 standard deviation below the mean, etc. So if the mean is 10 and the standard deviation is 2, and a student score is 8, what is the z-score? So you can calculate the z, and I'm going to try to do this. Let's see. Hopefully this is going to work. So we said you're looking for a z. The student score is 8 minus the mean of 10 over the standard deviation of 2. And I should write this out for you. So z is equal to x minus mu over sigma. So now we've got negative 2 over 2, which is a z-score of negative 1. What does that tell us? That person scored 1 standard deviation below the mean. I'm going to check back here to be sure that I The mean is 10, yep, and she got an 8, 1 standard deviation below the mean. If a student scores at the 84th percentile, what is her raw score? What is her z-score? We can look here. If she's at the 84th percentile, sorry guys, here we go. At the 84th percentile, we know that this is 50% plus 34. She's over here at a z-score of 1. And so that's how you would work with percentiles, percentages, and your z-scores. This is a good question here. Would you expect someone to have a score of 20? So if the mean is 10 and the standard deviation is 2, how likely is it for someone to get a score of 20? Again, I'm going to go back to this. Let's see. Yes, board. Let's draw a distribution. The z-score starts at 0. And we're saying in this case, the mean is 10. The standard deviation is 2. So the mean of 10, I can actually put that there. These are raw scores. And z-scores, so that would be a score of 0. 1 standard deviation out, right, a z-score of 1. That would actually get us to a raw score of 12, right? 10 plus 2. That's our standard deviation. At 2 standard deviations out, positive 2, we would have to add another 2 here. So we'd be at a raw score of 14. At 3 standard deviations out, we would have to add another 2. So we'd be at a raw score of 16. And the question was, how likely would it be for someone to get a score of 20? Okay, at 4 standard deviations out, we'd be at 18. And I'm going to go up here at 5 standard deviations. We're finally at a raw score of 20. So how likely is it for someone to get a score of 20 on this distribution, and this distribution of scores? That would be extremely, extremely unlikely. Okay. Okay, so the advantage of standardizing distributions is that 2 or more different distributions can be made the same. So if one distribution has a mean of 100 and a standard deviation of 10, and another distribution has a mean of 40 and a standard deviation of 6, if we transform individual scores into z-scores, the z-scores are all on the same scale. They will both have a mean of 0, they'll both have a standard deviation of 1, and they'll both be made into standard deviation units, and you can compare. So standardized z-values are converted from their original units, and they are now in the unit of standard deviations from the mean, and we can compare values. Bringing us to our last example, pull out your calculators one more time. We've got twin sisters, Haley and Lori, and they are intense competitors, but they never compete against each other. Haley specializes in long-distance running, and Lori is an excellent sprint swimmer. As you can see from the distributions in the table, each is the best in her event. Take the analysis one step further and use z-scores to determine who is the more outstanding twin. You might start by looking at the data and making an estimate. So here we've got the runners, and here's Haley, and you can see her time is 37 minutes. Good job, she's better than everyone in the field. And I have given you here, this is mu, the mean, and this is standard deviation. 2.08 is standard deviation, sigma. And in this case, the swimmers, we've got Lori, the other twin, with a time of 24 seconds. And she's done better than, again, everyone in her field. And this is mu, a 26.25, the mean. And the standard deviation, 1.71. Okay. So what you can do right now is find a z-score for Haley's time, is 37, and then find a z-score for Lori's time, 24, and we'll see which is the more outstanding twin. So go ahead and pause here and work it out. All right, and if you did work it out, let's go through it together. So we've got a z-score for Haley. I actually need to go and see how she did, because I don't remember. So 37, 39.5. She got a 37 minus the mean of 39.5 over the standard deviation of 2.08. Okay, and when you work that out, I'm going to do it here, 37 minus 39.5 divided by 2.08 gives us a z-score for Haley of negative 1.20. We're always going to round to 2 decimal places, so 1.20. And now we need a z-score for Lori. A z-score for Lori, she got 24 seconds. 24 seconds, the mean is 26.25, and we've got 71. So let's look at that. She's got her score of 24 minus the mean of 26.25 over a standard deviation of 1.71. So that is not right, what I just did. Let me do it this way. 24 minus 26.25, negative 2.25 divided by 1.71 is z-score for Lori is negative 1.32. You can read that. So the question is, which is the more outstanding twin? And this is a little bit tricky, actually. Who is the best athlete when you compare these two? Well, the answer is Lori. Why is the answer Lori and not Haley? Well, let's draw our distribution. We've got a mean here of 0, right? These are z-scores. This is negative 1. Here we are at negative 2. And we've got, let's see, Haley. This is like Haley's score here at negative 1.2. And then we'll put Lori's score here at negative 1.32. So Lori's is actually the more negative. Why is that a good thing? Well, these are athletes, right? Swimming and running. And you actually want a very, very low score if you're an athlete. You don't want to score at the mean. You certainly don't want to be above the mean in your swimming time or your running time. You do not want to be here. You want to be below the mean, and you want to be below the mean as much as possible. So in this case, Lori's score here is the more negative score, negative 1.32. She is the farthest below the mean, and so she's actually the better athlete of the two. Haley's score of negative 1.2, she's only 1.2 standard deviations below the mean. She's not quite as outstanding as her twin. So when you do calculate z-scores, you want to think about what scale are they on. Is this a scale that you want to be above the mean, like statistics exam score? You would like a very, very positive score. But time to run a mile, you'd like to be below the mean. Or depression symptoms on a depression scale, you'd like to be below the mean. So you've got to think about those things. All right, we have, I believe, finished everything we need, from this chapter, and take a little break and then come back and watch the second part. Thanks.